Long before humanity understood the true scale of the cosmos, people believed stars were the ultimate rulers of the universe. Bright, powerful, eternal. But hidden among those stars existed something far stranger than anyone could imagine. Objects invisible to the eye, yet powerful enough to distort the structure of reality itself. Black holes. They do not shine like stars. They emit no visible light. And yet their gravity is so extreme that even light, the fastest thing in existence, cannot escape once it crosses a certain boundary. For decades, black holes sounded almost impossible. Many imagined them as giant cosmic vacuum cleaners devouring everything nearby. But the truth is far more unsettling. A black hole is not simply an object floating in space. It is a region where space and time become violently warped. A place where the normal rules governing the universe begin to fail. At the center of every black hole lies one of science's greatest mysteries, the singularity. A point where matter may be compressed beyond comprehension, into a state where density becomes effectively infinite. Inside that region, our equations stop making reliable predictions. Physics breaks down. The universe becomes unreadable. Black holes therefore represent more than astronomical curiosities. They are natural laboratories testing the limits of human understanding itself. What happens when gravity becomes absolute? Can time survive under such conditions? And are there places in the cosmos forever hidden from knowledge? The modern story of black holes began in the early 20th century with a revolutionary idea from Albert Einstein. In 1915, Einstein introduced the theory of general relativity, transforming humanity's understanding of gravity forever. According to his theory, gravity is not an invisible force pulling objects together. Instead, massive objects bend the fabric of spacetime itself. Planets orbit stars because they move through curved space created by mass. 1 year later, physicist Carl Schwarzschild discovered a startling mathematical solution hidden within Einstein's equations. His calculations described an object so dense that escape would become impossible once anything crossed a certain distance. Even light would remain trapped. At first, many scientists treated the idea as mathematical fantasy. Surely nature could not create something so extreme. But over time, observations began telling a different story. Astronomers started detecting strange systems where visible stars orbited unseen companions exerting enormous gravitational influence. One famous example, Cygnus X1, revealed intense X-ray emissions coming from matter spiraling toward an invisible object too massive to be a normal star. Evidence slowly became impossible to ignore. Black holes were real. And they were everywhere. Scientists now believe millions may exist within the Milky Way alone. Even more astonishing, enormous supermassive black holes appear to exist at the centers of nearly all major galaxies. At the heart of our own galaxy lies Sagittarius A*, containing millions of times the mass of the Sun. Though hidden in darkness, its gravity controls the motion of stars across vast distances. In many ways, black holes are not merely destroyers. They are cosmic architects helping shape galaxies themselves. As gas and dust fall inward, they form blazing accretion disks heated to extraordinary temperatures. These disks release immense radiation detectable across the universe. Surrounding the black hole lies the event horizon, the point beyond which escape becomes impossible. Cross that invisible boundary, and every path through space leads inward. One of the strangest effects near this region is tidal stretching, sometimes called spaghettification. Gravity near a black hole changes so dramatically over short distances that anything approaching too closely could be stretched apart atom by atom. Matter becomes elongated into thin streams before disappearing forever beyond the horizon. Or at least, appearing to disappear. Because what truly happens inside remains unknown. And that mystery only deepens the closer science looks. For generations, black holes existed only in equations and imagination. Then humanity accomplished something extraordinary. In 2019, the Event Horizon Telescope collaboration revealed the first image ever associated with a black hole. Using radio observatories spread across Earth, scientists effectively transformed the planet itself into a giant telescope. Their target was a supermassive black hole inside the galaxy Messier 87, located tens of millions of light-years away. What emerged stunned the world. A glowing ring of superheated matter surrounding a dark central shadow. The image became historic not only because humanity had seen a black hole, but because it confirmed predictions made over a century earlier by Einstein's equations. Yet the discovery also intensified the mystery. Near the event horizon lies a region where gravity becomes so extreme that light itself can temporarily orbit the black hole. Deeper still may exist the singularity, a place where modern physics reaches its breaking point. And this creates one of science's greatest conflicts. General relativity predicts infinite density inside black holes. Quantum mechanics, however, suggests infinities should never physically exist. Somewhere between these two theories, something fundamental is missing. That search for answers has inspired ambitious ideas such as string theory, explored by physicists including Michio Kaku and Edward Witten. According to these concepts, reality may not be built from tiny point-like particles at all. Instead, every particle could be formed from microscopic vibrating strings of energy. Different vibrations would create different particles, forces, and forms of matter. Some versions of the theory even suggest additional hidden dimensions beyond ordinary space and time. Though highly theoretical, such ideas attempt to solve one of the most disturbing puzzles in physics, the black hole information paradox. Quantum theory says information in the universe cannot truly vanish. But traditional black hole models suggest anything entering a black hole may disappear forever. If information can be destroyed, some of physics' deepest principles may need rewriting. Black holes continue revealing surprises. Some spin at extraordinary speeds, dragging space-time itself around them through a phenomenon called frame dragging. These rotating giants possess regions known as ergospheres, where the structure of reality becomes twisted by motion. Scientists have even proposed that energy might theoretically be extracted from them. Other ideas emerging from Einstein's equations include wormholes, hypothetical tunnels connecting distant regions of space or perhaps entirely different universes. No evidence currently proves such structures exist. But the mathematics allows the possibility. Meanwhile, a completely new form of astronomy has emerged. In 2015, researchers detected gravitational waves for the first time, ripples in spacetime created by colliding black holes billions of light-years away. Humanity was no longer only observing the universe through light. For the first time, we had begun listening to the vibrations of space itself. Each signal carried echoes from ancient cosmic collisions that occurred long before Earth even existed. Black holes reveal a universe far stranger than imagination alone could invent. Invisible yet immensely powerful. Terrifying yet essential. Silent objects capable of reshaping galaxies and challenging the foundations of physics itself. Perhaps one day humanity will finally understand what lies beyond the event horizon. Until then, black holes remain among the greatest mysteries ever discovered, hidden regions where space, time, and reality seem to dissolve into the unknown.